everybody, in this video what I'm going to do is I'm going to go over the types of logic, deduction, induction, and abduction, and we're also going to take a look at arguments, validity, and soundness, as well as figure out what statements are. Let's get into it. Now I have a list here of 3 different types or kinds of logic. Here's the 3 most basic, if you will, species of logic: deduction, induction, and abduction. All of these come from the Latin word ducere, which means to lead. Like a duke, these each mean to lead in some different way. So deduction literally means to lead down. Induction, to lead into. Abduction, to lead away. You'll notice there is no seduction on the list, which means to lead astray. So that's not on this list. Occasionally I'll get someone do a fill in the blank on these questions and put there is such a thing as seductive logic. No, there's deduction, induction, and abduction, aka deductive logic, inductive logic, and abductive logic. The problem is these are all different kinds of logic and they have different criteria and they do different things. The main one that we're going to talk about in this course, like 99.9% of what we're going to do, is deductive logic. And you've seen it before. It's the most basic form of math based on the axioms that we have in place. So deductive logic is where you have logical arguments, and I'll talk more about what arguments are here in a moment, which can be measured in terms of validity and soundness. Basically, if the premises are true, it's impossible for the conclusion to be false. Like if you got all your material together, you know what the answer is going to be. And so, for example, on standard axiomatic systems, if I say 2 plus 2 equals x, solve for x, or what does 2 plus 2 equal, assuming we're using standard axioms, the answer is 4. Now you might do some equivalent of 4. You might say, oh, it's 16 over 4 as a fraction. Well, that's the same thing as 4. Basically, deduction works this way. If you have all the stuff together, there's no way that your conclusion could be wrong. 0% chance. If you know what 2 is, based on the system you're using, and you say 2 plus 2, you know it's going to be 4. Another example, deductive logic, geometry. I was using arithmetic there, and algebra. Geometry. If I say like a triangle has 3 sides, and then I see a figure that has 3 sides in 2 dimensions. Oh, it could be a square. Could be a circle. No, it's a triangle. That doesn't mean you know whether it's isosceles or equilateral or right triangle. You don't even need to know those things. If it's got 3 sides, it's a triangle. If it's got 8 sides, it's an octagon. If it's got 4 sides, it's quadrilateral. You might be thinking, oh, it's a square. Maybe, maybe not. Okay, what if it has 3 sides and it's a square? There's no 3-sided squares, there's no round circles, there's no circular squares. So the way deduction works is if you've got all the data, there's no way you can be wrong. That's one kind of logic, and we're going to focus mainly on that one. But that's not the only kind of logic that there is. There's some kinds of logic which it's possible to err, to make mistakes. There's a certain sense in which we can do that in deduction too for different reasons, but not based on the premises that we have or the information that we've got going in. So inductive logic, or induction, which literally means to lead into, is a kind of logic where arguments are constructed based on a given sample and then we generalize or universalize from those instances. So one example of this would be like polling data. When people interview people and say, you know, who's going to vote for whom, and then we say, okay, 90% of the people we interviewed say they're going to vote for this person, we can say, oh, this is the likelihood or the probability of this going to be happening. So that's inductive logic, where we're making probabilistic generalizations based on samples that we have. Meteorological science is done this way, based on what we understand about pressure systems, based on hurricanes that we've had in the past. We say this is the way that, based on the various instances that we've had happen in the past, this is the way we predict this is going to happen, but it's a lot more flexible. Same thing with polling. Like, we polled, we think here's what's going to happen, and then I think people saw that happen in the 2016 election. Here's what we think is going to happen going in terms of the polling. That didn't happen that way, because it's fallible. That is, it's possible to make mistakes even based on good data. And we say what makes an argument strong in inductive logic is that you have lots of data, you have lots of instances to support your position. An example of a weak argument in inductive logic or in statistics would be like, I interviewed one person, they said they're going to vote for this person, so I say 100% of people interviewed say they're going to vote for this person. Weak, because I didn't have a lot of instances to back up what I'm saying. Whereas a lot of laws of physics have this kind of inductive backup. How do we know if water is going to freeze at 32 degrees Fahrenheit? Well, because it's been measured multiple times that it will do that. Now, there might be counterexamples where it doesn't, based on, say, altitude or pressure or all kinds of other features. We haven't been at every single instance in the universe where water freezes at 32 degrees Fahrenheit. We can say, based on, hey, there's a whole bunch of instances where that's confirmed. So we can say, listen, if it gets down to 32 degrees, it's probably going to freeze. So that's the way induction works. High likelihood we're able to make declarations about things based on data analysis, all right? But it's probabilistic. It's not definite. We don't know with the same kind of certainty. Like that whole triangle has 3 sides. I'm looking at something with 3 sides. It's a triangle, 100% certain. You can't doubt it. Inductive logic, you can have high probability, 99% likelihood even. There's still a chance that you could be wrong. That's inductive logic. So abduction is where arguments are made as likely hypotheses to explain existing conditions. Okay, so what we do is abduction is we look at a situation and we think to ourselves, what made this happen? Now, like induction, it's possible for us to be wrong or mistaken much more easily than, say, in deduction. We might be right, but we might be wrong. So there's here, instead of probability with induction, we get necessity or certainty with deduction. We get probability with induction, and then we get likelihood of possibility with abduction. So what do I mean by that? Well, like criminal science is abductive. So like detectives solving crimes. You come into a crime scene, there's a murder victim on the ground, they've got a bullet hole in their chest. If you're a detective, were they stabbed? Maybe. But probably they were shot with a firearm. Well, maybe the bullet materialized in their chest somehow. Maybe. Or they were shot. So what you do in an abductor situation is you try and reason backwards from, okay, here's what I see. What made this happen? Criminal science is this way. Like, what made this happen? And we've seen it. That can be wrong. Have people been put on trial and convicted for crimes they didn't commit? Yes. Medical science is also often abductive. So someone comes in with symptoms and you try and reason backwards. Oh, they've got these symptoms. They must have this. They didn't have that. It came back negative. I guess we're going to have to do tests on something else. Medical science, we don't have an uproar over, oh, you said I was going to have this and I didn't. Based on the symptoms, we try and make abductions to figure out like what could be causing these symptoms. So that's also abduction as well. We do this often. Like if you came into your home, like you came in the front door and all your furniture was gone, I think it would be a wise abductive reason to think, oh, I've been robbed. Maybe there's other possibilities. Maybe someone was just like, no, I'm replacing all your stuff with better stuff. Like it's possible maybe you were moving and it was a surprise, or someone was getting you new furniture or whatever. All those things are possible, but abduction is where we try and say, when we come into a situation, we observe it. What made this happen? What are the conditions that made this possible? A lot of science is also abductive here. Geology looks at various stratifications of rock layers in the earth and says, well, then the earth must have been like this in the Pleistocene or the Pliocene or the Miocene or the Eocene or the Oligocene and so on. They're able to look at those things and say, here's what was going on then. Okay, here's what caused the Cambrian explosion. Scientists do this all the time. Astrophysicists will say, based on the way the universe seems to be expanding now, we can extrapolate backwards using abduction and figure out if the universe is like this now and it's expanding, we can kind of rewind the universe and see what it would have been like billions of years ago. Now, since that's abductive, it's possible that it's wrong. That doesn't mean don't trust it. It doesn't mean never abduce or induce. It's just that it's liable to be mistaken. We don't have the same kind of certainty as we do with deduction, like a triangle having three sides. There's no way we mess that one up. Induction depends on how much data we have to collect, and our abductive reasoning is only so good as the observations that we have to back it up. A lot of that feedback comes from induction. Now, the problem with this is, if you ever read like Sherlock Holmes refers to all of this, especially abduction, with the word deduction. These are the differences between them. Deduction is based on validity and soundness. If the premises are true, it's impossible for the conclusion to be false. Induction is where it's based on samples, and then those samples are universalized or generalized. We take a couple of instances. We say, okay, this happened a couple of times, so we can say probably this is going to happen. Then abduction is where we say, okay, here's what's going on. What caused this? So like right now, a good abductive argument would be like, okay, you're watching this video right now, so at some point Professor Burris in the past recorded a video in order to make this experience happen right now. That's a good abductive argument. It might be wrong. This could all be a deep fake, and this didn't happen. Maybe. So those are the different kinds of logic that we're going to talk about here. The main one that we're going to talk about and examine from here is deduction. Now let's get into some more aspects of deductive logic. I'm going to define some terms here. So first of all, let's talk about the notion of an argument. So colloquially, we use the term argument all the time to mean like we got into a fight with somebody. And sometimes people even in the domain of logic mean that as an argument, like we're fighting over two things, we're arguing. That's one thing. But an argument in logic, especially in deductive logic, is this. An argument is a series of statements, one of which the conclusion is affirmed on the basis of the others. And so the thing you're going for, like the verdict, if you will, is the conclusion. The stuff you use to back up the conclusion, those statements are called premises. So what's a statement? Which is also known as a proposition, hence the notion of propositional logic. A proposition or a statement is a sentence that can be either true or false. So that can be something that we say or something that we write down or type up. Something that we can utter in some way or can communicate in some way that can be either true or false. Something like Rex the dog is a Dalmatian. And maybe Rex is a dog, but Rex is a pit bull. In which case, Rex the dog is a Dalmatian is false. But if Rex the dog is actually a Dalmatian, then that's true. So a statement is something that can be either true or false. There are some things that we can say that are neither true nor false. And so that's the following four things that I have here. Imperatives or commands are neither true nor false. So if I say something like, go to your room, true or false, it's neither true nor false. An imperative is not a statement. Now, so-and-so said, go to your room. That can be true or false. Just the saying itself, go to your room,
is neither true nor false. That's the case with imperatives or commands. Also, inquiries or questions. If I say, like, is today Monday? True or false? Well, the answer to the question, today is Monday, it can be true or false. It is Monday or it's not. But any question is neither true nor false. They're devoid of any kind of truth content in that regard, or truth value. Proposals are suggestions. So if I said something like, let's get a puppy, neither true nor false. Now the answer to that can be true or false, but the proposal or the suggestion itself is neither true nor false. So imperatives, inquiries, proposals, neither true nor false, and therefore they are not statements because they have no truth value. And then the fourth kind is fairly obvious. That would be gibberish. So if I say blah, 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 true or false? Nope. The notion of truth value does not apply. So moving on from there, now we can talk about arguments that are comprised of statements, conclusions, and premises. In deductive logic, an argument is valid if and only if, given that the premises are true, it's impossible for the conclusion to be false. Now, we've already kind of talked about this, so let me also say too, the phrase if and only if, that'll come up again later in the semester. When you see if and only if, it's almost like an equal sign with words. So what that means is, if an argument's valid, then given that the premises are true, it's impossible for the conclusion to be false. And if the premises are true and it's impossible for the conclusion to be false, then the argument is valid. So if the premises are true, there's no way the conclusion to be wrong. Like, hey, we've got an object here, it's got three sides, it's a triangle, there's no way that could be wrong. That would be a valid argument. An argument is invalid if and only if, given that the premises are true, it is possible. It might not be, but it's possible for the conclusion to be false. So that means any kind of induction or abduction is automatically invalid. Now, that doesn't mean we shouldn't listen to it, but it means it's invalid in a specifically deductive sense. All the invalid means here is that it's possible it could be wrong. Not that it is wrong, but that it could be. So you'll hear people drop these words sometimes. That's a valid point. Colloquially, I'm fine with that. Someone says like a good point about something, like we should do this. That's a valid point. Fine. I wouldn't correct somebody in that. But in a strict deductive sense, something is only valid if and only if it's impossible for the conclusion to be false when it comes to looking at logical arguments. And then in deduction, an argument is sound both if it's valid and its premises are in fact true. So there's times where we can have a valid argument where it actually doesn't work in reality. And if an argument's invalid, it's automatically unsound, period. So those are the two criteria that an argument has to be sound. It has to be both valid and it has to be in fact true. So let's take a look at a couple of examples to see what I mean by that. So here's a valid argument. All triangles have three sides. The shape I'm looking at has three sides, so the shape I'm looking at is a triangle. Valid argument. If the premises are true, if triangles really do have three sides, and the shape I'm observing really has three sides, then there's no way the conclusion here could be wrong. And the shape I'm looking at is a triangle. Period. 100%. No doubt. Invalid argument means maybe, but maybe not. Like it could be, but it doesn't follow with necessity. That means, when I say necessity, that means it has a mustness, or that it must be true. Maybe. So the example I have here, some people win the lottery. True, they do. I'm a person, so I'm going to win the lottery. Maybe, but also maybe not. No, it's possible. So it doesn't mean that when I do win the lottery, see, I told you I was right. That means because I'm a person, because I can win the lottery, I told you I was going to win the lottery. That doesn't prove anything. So the fact that it's possible it could be otherwise makes an argument invalid. Sometimes you can have a valid argument, though. It's still unsound because the premises are not in fact true. So consider this one. This next argument is valid because all that valid means is if the premises are true, then it's impossible for the conclusion to be false. It doesn't mean the premises are actually true. So it has this. All sharks are ninjas. All ninjas are wizards. Now, if all that's true, if sharks are ninjas and ninjas are wizards, then it follows all sharks are wizards. That's a valid argument. This is why when people say the word, like they throw around the word valid, it might not necessarily be helpful. This is a valid argument. If the premises are true, then the conclusion follows. But I think we could say it's unsound because the premises are not in fact true. And then sometimes, here's another kind of a mistake, we can have an invalid argument where everything that you said to start is true, but the way that you put it together doesn't work. So look, here's an argument where the things that were said at the beginning were true, and the conclusion sounds like it should be true, but it's not. And I think it's obvious here. But what happens is sometimes people make arguments like this last one with stuff that we're unfamiliar with, and therefore it will sound more reasonable. Like, oh, that makes sense. So here it sounds stupid. So if I say all dogs are animals, all cats are animals. So since they're both animals, all dogs are cats. No, I could say all dogs and cats are both animals. That would follow. But say here all dogs are cats. That's stupid. Just because dogs are animals and all cats are animals does not mean that all dogs are cats. It's like a Venn diagram where it's just one circle. What's happening there is someone's doing something where the first 2 points are true, and the third point, the conclusion, sounds like it should kind of be true, but it doesn't actually follow from the premises. And then, like I said, when people are talking about things that are more technical, sometimes people use this kind of argument and will think it's true. Like if I said all particular asynchronous axioms are accretions from some point in time t, but also in time t we have accretions that are from the substratum of point B, well then what that means is that all substratums are accretions from point A. I just made that up and I used a bunch of technical language and it sounds like it's good, but based on what I said, just in the form, it's stupid. Nothing makes sense. In the example, it seems obvious, like that's wrong. But sometimes people are saying things that are technical and we don't recognize the stuff. Like with dogs and cats, it's obvious, but in other things, it might not be obvious. So someone might say something that we find confusing. We don't know if there's a mistake in there or not.
Well, that concludes this video on arguments and the kinds of logic and statements. What I'm going to do in the next video is I'm going to introduce the notion of informal fallacies. We'll spend the next 2 videos on that, and that's what will constitute the material for your first quiz.